Hi, my name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp 2, Lecture 6 on the delta method. So in this video, we're going to recap a little bit about the odds ratio, the relative risk, and these measures. And then I'm going to describe basically how you get the standard error and test statistics for these methods using this technique called the delta method. And then I'll briefly derive the delta method, but in a very general way, not in a highly technical way. Okay, so recall we had a setting where x was binomial, n1, p1, y was binomial, n2, p2, and then we could have this 2 by 2 table here as well. And we define the risk difference as the difference in the proportions. And this is because this is just an average, we can derive the standard error very quickly. We have the relative risk, which is P1 over P2, and the associated estimator P1 hat over P2 hat. And we have the standard error of the log relative risk, which is given here. And it's not clear how we derive that yet. And then we have the odds ratio, which is the odds associated with group 1, P1 over 1 minus P1, divided by the odds associated with group 2, which is P2 over 1 minus P2. The associated estimate is P1 hat divided by 1 minus P1 hat, whole thing divided by P2 hat divided by 1 minus P2 hat. And if you were to plug in the elements, the cells of the 2 by 2 table into that estimate, you would see that it's the cross product ratio, the main diagonal n11 times n12 divided by the off diagonal n12 and n21. We also gave you the standard error for the log odds, the estimated standard error for the log odds ratio estimate, and that is square root of 1 over the cell entries from the 2 by 2 table. This 1 over n11 plus 1 over n12 plus 1 over n21 plus 1 over n22. And then in any of the cases, the confidence interval is the estimate plus or minus the normal quantile times the standard error of the estimate. Now, a couple of notes are in order. First, in terms of the risk difference, we saw that maybe we can improve on this confidence interval by adding to the cells in a particular way. So hopefully you can recall back to that lecture. In addition, for the two other estimates, the relative risk and the odds ratio, you have the issue that the estimate here is the log relative risk and the log odds ratio. You add and subtract z1 minus alpha over 2 times the standard error of the log estimate, and then if you want an estimate for the relative risk or odds ratio, respectively, then you have to exponentiate the endpoints of the interval. Okay, so I hope you remember that as well. So this is our starting point, and during this lecture we're going to show you how to get these standard error estimates, or at least describe how they're obtained, and then hopefully you'll get a pretty good sense of how it's done and think very reasonably how it could apply far more broadly. Okay, so the delta method is a method that we can use to obtain standard errors for these instances where things aren't just a simple difference of averages or a simple average itself, like in the risk difference case, so like in the case of the log relative risk or the log odds ratio. So here's formally what the delta method states. It says that if you have an estimator, theta hat, and its estimand, theta, divided by the estimated standard error, if that tends to a normal 1 in distribution, then take a sufficiently smooth function f of theta hat, minus f of theta over f prime of theta hat times this standard error again, also converges to a normal 0, 1. So in a sense, what this is saying is sort of the asymptotic mean of f of theta hat is still f of theta. So if you want to estimate this function of theta, then the obvious estimate is f of theta hat. And this is saying that, well, maybe if we're going to use f of theta hat as an estimate of f of theta, we'd like a standard error. And it says, okay, we'll take the standard error that you would use if you weren't taking the function, standard error hat here of theta hat, and then simply multiply it times the derivative of f evaluated at theta hat. And that's what the delta method says. Okay, so let's go through an example. So theta, let's consider an instance where theta is P1. We're only going to consider x at this point. Our theta hat is P1 hat, x over N1. our estimated standard error, right? The standard error for x over n1 is square root p1 hat 1 minus p1 hat over n1. I hope that's not news to anyone in this case. And let's assume the f we want to estimate is log. So we're interested in log p1, for example. So f of x in this case is log x. Then f prime of x is 1 over x, okay? And then we know that theta hat minus theta over its standard error, that tends to a standard normal by the ordinary central limit theorem. In this case, theta hat is a simple average, okay? And we're just simply subtracting off its mean and dividing by a consistent standard error, so it converges to a normal 0, 1 by the ordinary central limit theorem. So then it's saying that the standard error, the estimated standard error of the log of the sample proportion is f prime theta hat times standard error of theta hat. So let's go through that calculation. So f prime of theta hat in this case is f prime is 1 over its argument. So in this case, in theta hat is p1 hat. So it's 1 over p1 hat times this standard error, which is square root p1 hat 1 minus p1 hat over n1. Rearrange terms and you get square root 1 minus p1 hat divided by p1 hat divided by n1. And so what this is saying is that log p1 hat minus p1 divided by this standard error, square root 1 minus p1 hat over p1 hat times n1, that tends to a normal 0, 1. So if I want a confidence interval for p1 for log p1, what I could do is take log p1 hat and add and subtract a standard normal quantile, let's say 1.96 for a 95% interval, times this standard error here, square root 1 minus p1 hat over p1 hat n1 hat, and that would be an interval. And so that works out to be very convenient. The only complexity in this whole calculation, and it was very mild complexity, was calculating the derivative of the function that we're interested in. The rest of it was simple arithmetic, and that's why the delta method is so powerful. Okay, so that actually doesn't give us a standard error for the log relative risk. And honestly, to do that in its full glory, you need a multivariate version of the delta method, which there is, but we don't really cover it in this class. So let's look at the asymptotic standard error for the log relative risk. Let's just kind of heuristically do it. So the variance of the log relative risk is the variance of log p1 hat divided by p2 hat. And so let's just say, so that is the variance of log p1 hat plus the variance of log p2 hat, because we're assuming that x and y are independent. The group 1 and group 2 binomial counts are independent. And so this, from going from these first three statements, this variance to this variance to this second line here, these are all exact equalities. We haven't done anything. Now, if we were to use our delta method estimate of the variance for each of these things that we calculated on the previous page, then we get 1 minus p1 hat over p1 hat n1 plus 1 minus p2 hat over p2 hat n2. And if we square root that is exactly the standard variance estimate for the log relative risk that we gave at the beginning of the class. Okay, and so that's where it comes from. And you could do exactly the same thing for the odds ratio. And you may have to do a little bit of arithmetic to show that it works out to be 1 over n11 plus 1 over n12 and so on. But the same exact rule applies, and it's relatively easy to do. There's one small bit of fudging that we're doing here, in that we're saying that delta method variances add in the same way that random variable variances add, and that is the case. That is the case. If you work out the multivariate delta method, the delta method estimated variances of independent things works out to be the sum of their delta method estimated variances worked out independently. But for the purposes of the class, this is not an issue. I think hopefully what you can follow is that for the log relative risk works out to be, for the variance of the log relative risk, we work out to needing the variance of the two component parts, log p1 hat and log p2 hat, and that we can calculate those associated variances with the delta method. Now notice, the delta method doesn't just give you a standard error and a variance calculation. It also gives you the asymptotic normality, so that not only do you get the variance estimate, but you get the inference too. You get the actual confidence interval that you want to create as well, or the hypothesis test that you'd like to perform. So the delta method isn't just the standard error variance calculation. That's just the neat part of it. The rest of it, the delta method also tells you can put the whole thing together as a confidence interval estimate. So for my final thought on the delta method, I thought I'd just show you quickly why it works. And it's very easy. It's surprisingly easy to prove. Now we're going to do a heuristic here, but the actual full proof is just not that different. So let's assume you have a large sample size, and the delta method is an asymptotic technique, so we can assume there's a large sample size. And if theta hat is close to theta, all right, then f of theta hat minus f of theta over theta hat minus theta, well, that should be approximately close to f prime of theta hat. Now, why is that? Well, on the left-hand side here, as theta approaches theta hat or theta hat approaches theta, either way, this is just the definition of a derivative of f. Okay, that's if you're not familiar with it, just go look up the definition of a derivative. It's the change in the function divided by the change in the arguments as the change in the arguments goes to 0. So this is exactly just the derivative of f. Okay, and then here we're assuming that theta hat is close to theta because theta hat converges to theta. It's a consistent estimate. Okay, so this first line's true. And let's just assume we multiply both sides by theta hat minus theta and divide both sides by f prime of theta hat, and we get this left-hand expression here and this right-hand expression here. And then let's just suppose we divide both sides by the standard error, the estimated standard error. And then what you get is that the right-hand side is roughly equal to the left-hand side. And so since the right-hand side converges to a normal 0, 1, the left-hand side should similarly converge to a normal 0, 1. And it also kind of gives you the heuristic of kind of why it works. If we assume f is a smooth enough function, right, and we appropriately divide by the derivative, then we're really kind of estimating the same thing as theta minus theta hat, as provided theta hat is close to theta. And that's ultimately why it works. It's nothing other than an instance of applying the definition of differentiation. And if you want the formal proof, if you really want that kind of detail, incidentally, by the way, my office is, we're on a medical campus, and I'm right near the emergency room, which is probably why you constantly hear the sirens going by. So those are the ambulances going to the emergency room, in case you were wondering. So anyway, if you want to prove the mean value theorem identically, right, if you want to prove the delta method exactly, what you have to use is a thing called the mean value theorem, and then you get a very formal proof of it. This heuristic is just based on the definition of a derivative, but if you use the exact mean value theorem, then you get the full proof. And that's it. And so in case you're wondering where, how in the world do people pull out these crazy standard errors for the odds ratio and the relative risk? Where do these formulas come from? It's a surprisingly easy little argument involving this quantity, this concept called the delta method.